Am I going now? I will begin with a word of prayer once I get up here. Heavenly Father, we thank you for this day, and thank you for the weekend, and it's time we have just to meet and to prepare for the test. Help us to use this time wisely, and help us to glorify you in what we do, Lord. In your name I pray, Lord Jesus. Amen. So I wanted to briefly go over the solution to quiz 5 here. And so, I mean, there's kind of, well, I don't know. Here, I have mixed feelings about quiz 5. So, like, I hadn't graded your team mission yet when I made quiz 5, so I didn't realize that I probably should have put more, like, practice basic problems in quiz 5. It would have maybe been helpful for you. But I didn't know that, so quiz 5 is actually kind of like, they're pretty tough problems for the most part. Not all, but some of them are kind of, come on, computer, wake up. A little bit tricky. So, let's see here. So I'll try to hand out the test in here right at the start of class, so you know time will be an issue. Does anybody have a problem with being here 5 minutes early for the test day? Like, is starting at 8:10 possible for you guys? Okay, so I'll try to hand the test out at 8:10. And I'll try to collect it at 9:10, so that way you have an hour. Which you'll probably need, right? Let me find, I will eventually find my way back to the solution here. All right. So I will post this in Canvas after class once I get a chance. All right. So problem 1 is just a plain old complex eigenvector problem. So you calculate the characteristic equation, and you find out you've got complex eigenvalues 3 plus or minus 4i. I select the 3 plus 4i, and that gives me this equation, v equals minus 2iu. I put u equal to 1. It gives me this complex eigenvector. And then the technique is to write down the complex solution, which in this case is e to the lambda t times u, which works out to be this, because e to the 3 plus 4it is e to the 3t times this cosine plus sine term. And then I just multiply through, and I keep all the real parts start, and I put all the imaginary stuff over here. And those are my separate real solutions. So this is a real solution, that's a real solution, and here's the general solution. That's how you do it. Any questions about this? Okay. So I don't think that one was the super complicated problem. That was not what I was talking about, all right? I'm talking about this one. This one's a bit much for an in-class hour test. If if I have 10 other problems on the test, this is a bit much, right? So yeah, so probably shy away from this because we're in Monday, Wednesday, Friday format. If it's Tuesday, Thursday, I might consider it, but anyway, not that it's impossible or anything, but it does require attention to detail. So I start by finding the fundamental solution matrix here, which I get from looking at, again, it's a complex eigenvector. This time the eigenvalue is plus or minus I, and so it's a little bit easier in some sense because that's my fundamental solution matrix. I know for variation of parameters I need to invert it, so I use the usual inverse formula. I get that, and then the particular solution, as we derived, is the integral of x times x inverse times f, and it's pretty neat how this all works out, because when you do the integrals, after you multiply, you get sines and cosines and such. And so this integrates to this, and that integrates to that. If I was to add a constant here, that has the effect of adding in a copy of the homogeneous solution, but I didn't. So anyway, after I do the integral and then multiply by that, the multiplication does take a little bit, but after you do it, you should see sine squareds plus cosine squareds arising and things canceling out. And lo and behold, it simplifies down to just that. So that's kind of neat. So yeah, and so the solution is a constant times the first real part, constant times the imaginary part, plus this particular solution. That would be the solution in this case. So, all right. But again, I don't see myself asking this problem on the test because I think it's a little bit too long. This one also is too long for the test for kind of other reasons, just because I was trying to make it nice by giving you numbers, and my kindness was actually cruelty, as you can kind of see. So anyway, it's the same thing again, though. This is the complex eigensolution. That's the real part. That's the imaginary part. And then there's a generalized complex eigensolution, the other one. That's a generalized complex eigenvector. And so again, I do e to the lambda t magic formula times the complex eigenvector. And that this time gives me u2 plus tu1, which is this and that. And again, I collect all the real stuff together and all the imaginary stuff together. And those are my separate real and imaginary solutions. That's how you can end up with like t times cosine or t times sine in a solution to one of these things. And yeah, there it is in all its glory. Nobody wants to grade this. And so there's a way to make this problem less obtuse, which is to not actually give you the details of the vectors, but just write them as like a plus ib. Like if I instead make it more symbolic, like problem 23 in the mission, I think it was. But anyway. Now this problem I think is reasonable, actually. This problem would not be a completely inaccessible question for a test. This one's actually not too bad. So here I give you a pretty sizable hint that we can rewrite e to the ta as, e to the 2 times the identity matrix plus this n, which is what's called a nilpotent matrix because its third power is 0. And anyway, so I can use the formula which was given. And the thing is, past order 3, all these things are 0, right? So you do need to know the definition of the matrix exponential as a series. And you do need to not be afraid to try to calculate that. You've had calculus too. You know what a series is, and you can do those calculations, all right? So that is part of this course. Anyway, so this is how it works out too. I left the e to the 2t outside because it doesn't give me joy to write e to the 2t 1, 2, 3, 4, 5, 6 times. But there you go. And once you have a fundamental solution matrix, this is something that you should have learned, but I haven't emphasized as much as I would have liked to perhaps in here, which is once we have a fundamental solution matrix, if we take a constant vector times the fundamental solution matrix, that is our general solution. See, because a constant vector times a solution matrix is a linear combination of the columns of this matrix. Each column is a solution to the differential equation. And so this, for an arbitrary c, is an arbitrary linear combination of solutions. And as such, I can fit any initial condition. So when we have e to the ta, it's especially nice because e to the 0 is I. So when I plug in r of 0, I find out that the constant vector I want to put here is simply the given data vector, 1, 2, 3. And so I just take this times 1, 2, 3, and that gives me the solution in this particular case. So that was nice. But hey, that's it for the quiz. Do you guys have questions? Yeah. So probably question 1 or 4 probably going to be somewhere on the test? Could be. I think that's fair, right? Give me a second here. Let me look at my archives. See if I can find something here. All right, first of all, let me open, where was it? Where'd you go? Well, there it is. Let's open that. Let's see. Trying to find an old set of homework or something here. Ah. Let's see here. Just a second, guys. I'm trying to find some old stuff to look at here. Ooh. Oh, no, no, no. That's not the one. Oh, nope, 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 nope. Oh, maybe. Nope. Arr. No, that was not the one. I will eventually find it. Oof, Laplace transforms. We're not there yet. Yowzers. Well, fine. So like here's a old homework set. You know, this one's not too bad. Let's see here. Uh-oh, Java problems. Oh no.
You gave him 115 homework problems?
Yeah. I could fix it. I can give you guys more. It seems like, from what I've seen, that if I give you 25, you're only going to do 20 of them. So, roughly speaking. I mean, you turned in more than 20, but like 20 are finished. If that makes sense. I don't know, something like that. But
That's so aggressive.
yeah. Well, I do believe in an adversarial pedagogy. So, no. No, I do hope you guys get more of the next mission done. Like, start earlier. There's obviously kind of like some problems towards the end. But anyway, so what was my point here? I wanted to see if I could find a decent. So here is a, ooh, goodness gracious. So this would be an example of what I would hopefully not put on your test in its current, like, there might be a 3x3 problem on the test, but it wouldn't be, unless I do something terribly, horribly wrong. Like, it's not going to happen. I'm going to check beforehand for you guys. This won't happen, right? This is homework, so it's not a test, right? But, like, if I do put a 3x3 on the test, it should either have, like, you know, one nice real one and one nice complex one, or 3 real ones that are reasonable. And it may be that there's something nice about the 3x3 matrix which makes it so you can calculate it somewhat easily. Like this one, for example, is actually very easy to calculate the characteristic equation because you notice the 0 down here? That makes it so that there's a property of determinants. You can say it's the determinant of this 2x2 block times that. Like this is an identity for determinants I shared with you guys. So if you use that identity, that can be very labor saving, right? So if we have the determinant of block matrix, like if I got A here and B here like that, then this is equal to the determinant of A times the determinant of B, right? So, yeah, I used to have graders for this course more reliably, so like I could collect more homework, but graders are in short supply these days, so it's a little bit harder to arrange that. Excuse me. This one here, I have, goodness gracious, A, B, C, D, A, B, C, D, E, and I think I said they could use technology. But so these are some like, you know, actually decent questions in terms of like the numbers, because apparently this one has, you know, nice eigenvalues. So anyway, let me stop talking about this. I don't think I'm making much headway for the discussion. Let's go back to, if I can find it. Where was it?
Excuse me, Professor.
Go for it.
For the previous problem, for the other two values of lambda, would you use the quadratic equation to find those?
I would complete the square, but you could use quadratic equation, yeah. But yeah, again, like that's fine for like it's fine for outside of a test, but I think that I wouldn't be aiming for that on a test unless it was like a 2x2 system, in which case it's a little bit more manageable if that happened there. But for 3x3 with approximate, anyway, I do think this is kind of a nice example, though. You see just a little bit more that this wasn't really in your homework, but this is nice to see. So I use technology to find eigenvectors to write down the solutions, right? So like number one, I've got solution 1, 2, 3. This is what we expect for a 3x3 system. We have to have 3 independent solutions, right? And if you look, I have find a fundamental solution matrix for each of the systems given in the previous problem. So like to use those 3 solutions to write down, oh, come on. Rats. So that's part, man. All right, so this is it. Like this x here, I think corresponds to, oh, I give up. I can't read this solution that fast. I'm sorry, guys. I'm going to stop trying to do this. You gotta know when to bail. Where it was, I'm trying to find the solution to your team mission. There it is. So one of the things I wanted to mention is I did not spend enough time on this, so like I'm not going to put this on the test if that's okay with you guys, because I don't think it's fair. So in contrast, we did spend like an hour and a half of class time on working 3x3 eigenvector problems. So I think that's a much more reasonable question to put on the test, provided that the cubic equation is not too like horrible, right? This is what I was trying to talk about and trying to find another example of, but I failed at the moment to find you another clear example of it. But so here, I gave you the vectors and the algebra they solved, and I just asked you to write down, you know, like the solution that follows. And so I think this is like a better way to ask this kind of question, as to not burden you with, you know, components of four-dimensional vectors like it was on the quiz, right? Like that complex one on the quiz is a bit much in terms of the writing. But this one here, a lot of you have a lot to learn from what I saw on the team mission, right? Like a lot of you haven't quite processed how we're doing this yet. And so the key is that we're always using the magic formula, and we're multiplying by like the vector that's given and using the algebraic conditions that are given. So like for an eigenvector, when I multiply an eigenvector times these things, they're all 0, because like a minus 3i is equal to 0, which makes any higher power of a minus 3i acting on that vector u1 be 0. In contrast, u3 is a generalized eigenvector of order 2, so when it hits a minus 3i, you're given that it gives you back u1. So you get u3 plus tu1. And for u2, it's actually a generalized eigenvector of order 2 as it happens. I mean, order 3 rather. And so when I take u2 and I feed it to the magic formula, I get the u2 from the I. I get a minus 3i times u2, which is u3, right? And then I get this t squared over 2 a minus 3i squared times u2, which works out to u1. But there's a 1/2 t squared from the formula, which is why I have 1/2 t squared u1. Now some of you are just like writing t times the vector or something. I don't know what that's coming from, but like you have to think through the magic formula in these kinds of problems. If you have complex data, you write down the same idea in the complex case, and then you take the real and the imaginary part of it to find real solutions. So that was that. Any other questions about the team mission now that we've had some time for it to kind of sit and think about it some more? Nobody? All right. Let's see here. Let's just take a gander here. Some ancient homework 10 years ago, right? Let's see here. Oh man, look at this. Show y equals tangent. I'd be scared to ask this because I know what would happen in here. Show y equals 5 tangent 5x is a solution to that differential equation. So, goodness gracious, we hadn't have any question like this, which is for shame on me. What does it mean to be a solution to a differential equation? What do? You show that if you plug it in, it works, right? So I didn't ever work a problem like this, but we've done this idea like 2 or 3 or 4 times in class where I have proposed a method of solution, right? And then we plug it in and see what it takes to make it work, right? So this is kind of just a specific instant of that. So that would be a reasonable test question, although it's somewhat unlikely. The larger point here is not for me to tell you exactly what's on the test. The larger point is for me to try to communicate to you that like the test is about a certain set of concepts and you need to understand those concepts, right? So, and be ready to solve problems that are like the problems we solved, but they could, I suppose, be different. This one here is tough. Like this is x cubed plus y cubed equal to 3cxy. The folly of Descartes, huh? I mean Descartes. Sorry, there's a guy who called him Descartes in one of my courses as an undergraduate, and it's still in my brain. But if you calculate the implicit derivative of that, you get this, which is that, which gives that, which gives that, which gives that. Anyway, it takes a while, but you can eventually eliminate the c and just find a differential equation which is true for every member of the family, right? Why would that matter? Like, what if you wanted to find orthogonal trajectories? It might be nice to have the one without the constant in it to work with, but again, let me go on. This is a kind of weird problem. How about this one? This one's less weird. Like, this would be a nice, reasonably decent test question, right? dy dx equals 2y plus 3 over 4x plus 5 squared. Separate, integrate, you know. That's an implicit solution. Then to find the explicit solution, I solve for y. Great, that's not a bad example. This one here, find the implicit general solution. So separate, integrate, right? We do need to know the integral of du over 1 plus u squared is inverse tangent. We should all know that, right? That's definitely integration that we know. All right, there's another example. What's up with this problem here? We've got square root of 1 minus y squared dx plus the square root of 1 minus x squared dy equal to 0. So I guess you could you do this exact as an exactly problem? I don't know. What's the y derivative? Oh, the y derivative of this. Is the y derivative of this equal to the x derivative of that? Certainly not, right? The one is a function of y, the other is a function of x. So the closed condition doesn't hold. This is not exact, which means that this is actually a separation of variables problem, so you do it. And oh, look, the integral, that's inverse sine, or arc sine, perhaps, if you like. So that's not a bad problem. I think this was actually a problem in your homework, right? dy dx tangent y equals secant x. So you find the yield integrating factor and multiply, get yourself a secant squared, and reverse product rule, integrate both sides. Woohoo! That one's not bad. Here's another one. So let's see, this one, I think again, it's a linear differential equation, but it's kind of written in a kind of yucky way to start with. So you divide by the leading coefficient of the derivative, and it gets you to here. And then integrating factor ends up being x plus 1. Multiplying by that gets you here, which then you reverse product rule, integrate both sides, solve. Let's see here. Yeah, let's see here. Oh, I think I gave you guys this one. Whew, hey, look at this. Maybe I'm recycling this homework. Looks like it's a strong possibility, right? They're starting to look a lot like the team mission, aren't they? Yeah. All right. So anyway. Oh, here's a good problem. I think we worked this one out, didn't we? This is the substitution. Is this the same substitution problem we had in the team mission? I think it is. Right? So if we have, I say let v equal something, you work it out. Anyway, let me put this away. If there aren't any questions, I'm going to put this away. No? All right, so I have been working on writing your test. I'm not terribly happy with what I have at the moment, but I'll tell you what I have. And then I'll let you guys talk to your groups or whatever. All right? Unless you guys got questions, which you can ask. Let's see here.
Can we get a note card on the test?
Yep, you are allowed a 3-inch by 5-inch note card. That's a good question. So
Both sides or just one?
both sides is fine. Only 2. No 4 sides.
I saw something online where someone said, a professor said you're allowed to have a 3x5 card, but he did not specify units. And someone brought in a 3-foot by 5-foot reference sheet.
Yes, on my course planner it says 3 inches by 5 inches. So yeah. So those are the dimensions. But thank you for that. Let's see here.
Remember the 3 by 3 inch cube?
Nope. 3 by 5 inch card is what we're looking for here. Let's see here.
Do you know about how many questions there are going to be?
Oh, there's definitely enough questions. But I think I currently have 6 pages. I mean, there's a lot of white space. So that doesn't really tell you anything, but here I will tell you. Like, so here's my current here's the current rundown. All right, and this is likely to change because I'm still editing it. So problem 1, it's like here's the net force on a mass with position x is given by a particular formula, and here's I give you as a positive constant in the formula. Find the velocity at time t, given that the velocity is equal to v0 when t equal to 0. So it's a force initial velocity problem. Problem 2 is find the explicit general solution of a first order differential equation. Problem 3 is find the implicit general solution of a first order differential equation. Problem 4 is a symbolic eigenvector type problem that involves both real and complex. And I would say it's somewhat similar to like problem 23. I would say it's kind of a mashup of like problem 23 and the problem on the quiz that I don't like because it's too messy, the 4x4. Which is not to say it involves a complex, generalized complex eigenvector. I don't think it has that in there. But it does have some complex. Problem 5 is a token calculate the exterior derivative of a form and interpret it question. It's not worth a lot. Oh, to give you the point values at the moment, 15 points for problem 1, 20 points for problem 2, 20 points for problem 3, 10 points for problem 4, 5 points for problem 5. Problem 6 is solve a first order differential equation by a substitution. Of course, the substitution is given, as I told you guys I would. 20 points. I give you a whole page to work that out. Problem 7. Here's a vector field. I give you a vector field. Part A. Show the vector field's conservative by finding a potential energy function for which f is equal to minus the gradient of the potential energy function. I use symbols, like the upside down triangle, and a minus. Part B. Solve a particular first order differential equation in Pfaffian form. So part B is solve a differential equation. Part C is find the Cartesian equation of the integral curve of f through a point. Let's talk about that. So I talked about this early on as a motivating, well, hopefully a motivating problem for this course. And so I do expect I would test on it, probably on both concepts, right? So if we have f is PQ, right? So the integral curve for f solves, let's say dr dt is equal to f of r of t. So this is, you know, t maps to r of t, which you could also write as x of t, y of t. This would be, you know, a parameterization of the integral curve, right? Parameterization, you know from Calc 3, it's when you give functions of time for both x and y, right? And so to actually find this, what does that mean? That means you have to solve dx dt equals to p and dy dt equals to q, right? So if you want to find the parameterization of the integral curve, you have to solve those two differential equations, right? And at the start of this course, we had no means to do that, right? Because how did we actually solve those kind of differential equations? What was our technique for solving systems? Substitution? Nope. No. So like if I had dx dt, for example, equal to x plus 3y, and I had dy dt equal to, say, minus 3x plus 7y, how would I solve that system? What would I do? And can we be confident we can solve any such system at this point? We can, right? So the solution is e to the ta, where that's the matrix exponential, and here a is equal to what? 1, 3, minus 3, 7. Now I don't know. I just made these numbers up, so it might not be a reasonable test question, right? Because there could be the eigenvalues could be 3.47564, and the other eigenvalues 7.567. I don't. Who knows? But the point is, we do have a method for solving these now, right? The eigenvector method. Great. Now, so to find the integral curve directly, to find a parameterization of it, we have to solve this system, right? Great. But what's the other thing we did? Or we can find a Cartesian equation for the curve. And how would we do that? We're trying to, so basically just look at dy dx is equal to what? It's dy dt divided by dx dt, right? But those respectively are q and p. So if we want to find a Cartesian equation for the integral curve, we don't actually have to solve the system of differential equations, right? We can solve this much more friendly, easygoing, possibly easygoing, you know, separation of variables problem, perhaps, right? So we've looked at both of those. If you look back at the team mission, you'll notice that I've asked about both. Come on. The computer has decided to save its power on me. How dare it. So like getting back to problem 7 on my current version of the test, part A, show the vector field's conservative by finding a potential energy function. Part B, solve a given first order differential equation in Pfaffian form. That means written with the dx and the dy, right? And then part C, 10 points, find the Cartesian equation for the integral curve of f through x naught, y naught. Right? So what does that mean? That means you need to look at the differential equation, the vector field you're given, and you set this up, and you try to solve it. Which you can do, right? Because it's just dy dx equals to a fraction of functions of x and y. Problem 8. Oh, so that previous problem was worth 25 points. 7 points for the potential energy, 8 points for solving the first order differential equation, and 10 points for finding the Cartesian equation for the integral curve. Problem 8 is 20 points. Find the general solution of a system of differential equations by the eigenvector technique. At the moment it's 2 by 2, but I'm leaning towards making a 3 by 3 problem. Problem 9, consider the vector field. Find a parameterization of the integral curve by finding real solutions of this system of differential equations. So in other words, for problem 9, I kind of walk you through getting from here over to here in the problem statement. Whereas in the other problem, I do not tell you to do this. That's up to you to have paid attention and to have understood. And if you haven't, well, then you're kind of at a loss how to do that problem, but such is life. Hopefully not, though. We've had this conversation now, so you'll get it. I mean, it's more of a monologue, but anyway. Problem 10, here's a matrix. Calculate the matrix exponential. So here, I really intend for you to calculate from the definition of the matrix exponential. Now, this is my current version of the test. I'm not terribly happy with it because it's missing some things that I kind of want to test on in terms of like the theory of differential equations. But it's a good start at least. Now, there is no energy method on the test, like the energy level thing. I will not test on that for you guys this time because I didn't get to it in class, sadly, during the regular. I didn't do enough of it in class, is what it boils down to. So anyway, any questions?
If you change the test, would you add questions or replace questions?
Yes. So I don't know, like, but probably 6 pages is enough for an hour test. Yeah. I don't want to. I mean, if I could cut it back to 4 pages, that would cut my grading by 50%. That'd be good. The question is, can I do that reasonably and still see if you guys know your stuff? I mean, maybe if I just ask one really difficult question, that would be enough. You know, just one question with like parts A, B, C, D, E, F, G, H, I, J. No, I'm just joking. Just do your best, and if you've spent time doing the homework and you've understood the lectures from class, then you should have a shot at it. So, in any event, I see you guys Wednesday. I'm going to cut off.
That are on the test, problems that are found in the
The problems that are on the test involve problems like the problems on the team mission,
Like, are there any
or problems on the quiz, or problems from my notes, or problems we covered in
So there
lecture.
could be problems on the test that are like to problems in the mission.
Yes, that's possible.